Right, well, hello everyone, and welcome to the Northeast's first feature talk. My name's Sam. I'm the chair of the Northeast branch of the Institute of Physics, and of course this being a very unusual time, I'm just starting my second year as the chair, and this is the first time I've had a public engagement where I've had to actually chair a talk. So please give me some thing if I'm feeling a bit rusty at this. We have a great talk coming up. Obviously, I'm not going to dwell on the fact that we've had some difficulties over the past 18 months, but I'm going to look forward to the fact that we are actually now getting to the point where we can actually start really doing many more of the sort of things that we love to used to do. I know the committee up here in the Northeast is really looking forward to getting back out and really engaging with the public and our members, doing many more events like this. I have a couple of housekeeping issues just to check out with you. Obviously, we're doing this over Zoom. If you have any technical issues, you can let us know in the chat box. You can display the chat box by using Alt-H if you're using a Windows computer, or Option-H if it's a Mac. If you'd like to ask any questions outside of the Q&A box, then you can raise your hand and unmute them. Well, so if you'd like to ask any questions outside the outbox, raise your hand. To do that, it's Alt-Y or Option-Y if you're on a Mac. And finally, that was it for that. So I'm really doing this very badly. I do apologize. I said I was out of practice. Anyway, without further ado, I would love to introduce our two speakers. Chris Harrison of Newcastle University and Nic Bonne, Nic of Portsmouth University.
Okay, I think we're ready to go. Someone can interrupt me if something's going wrong. So hello, everybody, and I'm delighted to be here with my colleague Nic to talk to you about how we can take a multisensory approach to exploring our universe. Now, before we get started, I want to give you our take-home message, just in case you fall asleep or we have a blackout or something like that. Let's get our take-home message all ready. So there's a huge potential for multisensory approaches to astronomy, education, and research. And this has benefits for both accessibility as well as scientific discovery. So that's our key take-home message, and hopefully over the next 45 minutes or so, we will convince you of that fact. So a little bit more about your speakers today. So I am Chris. I'm currently based at Newcastle University. My main job is as an astronomer. I use telescopes on the ground and in space to try and understand galaxies and the supermassive black holes that reside at the center of them. But when I'm not doing that, I'm always exploring new ways to make astronomy more engaging, more accessible, and new ways that we can explore astronomy and make it more accessible. And today will be a bit about that work and how I've been exploring how to use sound to represent astronomy. And then Nic, would you like to introduce yourself?
Yeah, so good evening, everybody. So I'm Nic. I am also an astronomer. So I have a background in galaxies research, but my job nowadays is mostly outreach and public engagement. So I basically take the science that the astronomers in my department do, and I work out ways that we can communicate that to the public. So to schools, to people at science centers, things like that. A big part of my job at the moment is leading a project called the Tactile Universe. And that's a public engagement project where we're looking at ways that we can communicate topics in astronomy to people who are blind and vision impaired. Now, I should also say, I'm a little bit unusual as an astronomer because I'm somebody with a pretty severe vision impairment. We'll go into why that's a little bit unusual as we progress through the talk.
Thanks, Nic. So we're going to start our talk just reflecting on what we can see in the universe when we look up at the night sky. So for those of you who have full vision, you can go out in the night sky. If there aren't too many lights around, you can look up and see the pinpricks of the stars against the blackness of space. Now, basically all of the stars you can see in the night sky are inside what we call our Milky Way Galaxy. So that's a group of stars. So we want to get you going and want to check you're awake. So we've created a little Zoom poll for you to do to see that you're listening to what we're saying. So the question that we're going to pose to you in a moment is, roughly what percentage of the stars in the Milky Way Galaxy can we see with the naked eye? So if we go out, we have a clear night, we have full vision, roughly what percentage of the Milky Way stars can we see in the night sky? So there'll be four options. A is 20%, B is 2%, C is 0.02%, and D is 0.0002%. So in your own time, don't worry, your answers are anonymous. Please answer our Zoom poll and we'll see what you think. Hopefully that's popped up for you, so you can click on your answer. Apparently I'm not allowed to vote, my message says.
I'm not allowed to either, Chris.
So we'll give you a few more seconds to submit your answer. Okay, so maybe we can close that now with me and see what people said. If you can give us the answers that were submitted. Ah, we see, I thought you'd know the answer. So most of you have gone for these very small numbers, which indeed is the right answer is the last one, D, 0.0002% of the stars in the night sky that's how many stars of the Milky Way we can see in the night sky. That's about 1 in 500,000 of the stars in the Milky Way. So we can see about 2,000 stars on a good night in the night sky, which is of the 100 billion stars that are inside the Milky Way. So not many, but that's not it, is it, Nick? What else
No,
is
it
going
isn't.
on?
So it's pretty amazing, really, when you think about it. Most of the stuff we can see in the night sky using the naked eye is inside of our own galaxy. It's actually really, really difficult for us to see anything outside of our own galaxy. And that's something really important to remember. So to see other galaxies, to see further away, we generally need to point telescopes at patches of sky. And to see the average galaxy, we need to take exposures with telescopes. So let those telescopes collect light for anything from minutes to sort of hours just to see those galaxies properly. It gets even worse though. So there's a particular example I want to talk about, and that's a special observation that the Hubble Space Telescope made, and it's called the Hubble Ultra Deep Field. So the Hubble Space Telescope pointed at a very specific patch of sky. This patch of sky is the same distance across as 1/10 of the full moon as it appears in the night sky. So a really, really tiny patch of sky. And Hubble took a total of 11.3 days worth of exposures of just that patch of sky. And when they analyzed the data, when they put everything together, the scientists who'd made those observations were able to count 10,000 individual galaxies just in that tiny patch of the night sky. And so that observation allowed us to estimate how many galaxies there must be in the universe. And that number is something around about 2 trillion. So we think there are 2 trillion other galaxies in the universe outside of our Milky Way. But just imagine if we can look at a tiny patch of sky like that, admittedly for a very, very long time, and see that much extra stuff, it makes you wonder just how much other things there must be in the night sky that we just can't see using our naked eye. And just to build on that idea, it's also worth remembering that only a tiny fraction of the overall stuff that makes up our universe is actually regular matter that can be observed. So regular matter makes up about 4.6% of the total sort of energy and mass budget of the universe. We also have this other stuff called dark matter that we can't see directly, and stuff called dark energy that has a really big influence on how the universe behaves, how the universe has evolved since it was first formed. But it's really just a tiny fraction of the universe that's made up of stuff we can actually see. And quite a lot of that stuff isn't actually luminous. So of that 4.6%, a lot of that matter is going to be in dust clouds or planets or gas clouds, things that aren't actually illuminated. Only some of that stuff is going to be in stars and actually be really, really easy to spot. As well as that, it's worth remembering that the human eye can only see in the visible spectrum. But there's so much more to the electromagnetic spectrum outside of the visible range. The visible range is just a tiny, tiny fraction. Moving towards the red end of the spectrum, we move into infrared, microwave, radio, and other longer wavelengths. Going towards blue, we look at ultraviolet, X-ray, and then even gamma rays. So there's so much more stuff that emits in wavelengths outside of the visible spectrum that we need to use special instruments to actually observe.
Yeah, thanks, Nick. And indeed, if we start studying space with those parts of the electromagnetic spectrum that are invisible to the naked eye, there is a lot we can learn. So just to give you one example, I'm showing on the screen an image of a galaxy called Centaurus A. This image was taken with a visible light telescope, so it collects the type of light that we can see with our eyes, but because it's a giant telescope and exposed for a long time, it's a lot more sensitive than what our eyes can see. And in this image, there's some background stars, but then there's this big bulge of light in the center, which is the cumulative light of all of the hundreds of billions of stars inside that galaxy. But then there's some strange dark patches going across that bulge of light. But we can learn more if we go beyond the visible and look at this, for example, in infrared wavelengths. So this is moving beyond red into the infrared light. So I'm now showing you a picture from the Spitzer Space Telescope of the same galaxy. Now we can't see that bulge of stars. All we can see is that this band of dark that I saw is now glowing. And this is a band of dust that's inside this galaxy, and it glows in the infrared. It's warmed up by the starlight, and then it glows in the infrared. Now in the image, it's represented as a red color, but of course, that's just a fake choice. The image would be invisible to our eye because our eyes cannot see the infrared. But what about the same galaxy in the radio? Well, something remarkable happens. You don't see anything like we saw in the optical infrared. Now we're seeing these plumes of energetic particles coming above and below the galaxy. We call these jets of charged particles, and they're being launched from a supermassive black hole at the center. In this image, it's shown as some pink, but of course, pink is a fake choice. Our eyes cannot see radio wavelengths, but we learn so much by studying the galaxy in radio wavelengths. And now thinking about X-rays, again, we can see these beams of charged particles. This time they're a lot narrower in the image, coming from the center and going over large distances. And around those, we can see bubbles of hot gas in an X-ray image. This time the choice was made to make it blue, but of course, it's not really blue. It's a choice that has been made. Apart from the optical image, these are all basically fake color images. But not just that, the radio image wasn't even taken as an image at all. The data to make a radio image isn't recorded as an image at the telescope. Instead, it's lots of individual dishes. They're like satellite dishes spread over the ground, and each dish records the radio signals as they arrive at the telescope. And there's big data tables recording how that signal arrives at each of these dishes. Somebody then takes that huge data table, does some complicated computer algorithms, where choices will need to be made, and tries to reconstruct an image from that data. So let's just recap about what we've been talking about. We've discussed most of the universe is completely dark. It doesn't emit any light whatsoever. And that light that is produced, mostly it's invisible to us. Mostly it's not in the visible part of the spectrum. We need special telescopes to detect that light, just because it's either so faint or it's outside of the wavelengths of light that we can see. But despite that, we nearly always make the choice to represent the things in space as fake color images. Or in the case of scientific analysis, we turn that data into graphs or some sort of plots. But Nick, we don't have to always do that, do we?
No, we absolutely don't. And there are definitely some advantages to using other senses, like our sense of hearing or our sense of touch, or even in some really unusual cases, our sense of smell or taste. A really good example of how where our ears can be particularly useful is in actually picking signal out from noise. And so an example of this would be standing in a really busy environment. Say you're standing in a train station, you're trying to find somebody that you're supposed to be meeting. If that person calls out to you or says something from quite a distance away, your ears rather, are good enough at picking out signals or noises that they can recognize, that they'll be able to hear that person, even though there's all of that background noise, maybe hundreds of other people talking at the same time. So there are really, there are some quite significant advantages to starting to look at astronomy, to look at how we think about astronomy, how we think about astronomy data, but using sensors other than just the visual. Okay, and there are actually, so I mentioned before, I'm a little bit unusual in that I'm an astronomer with a severe vision impairment. So there are only a handful of other professional astronomers in the world at the moment who would either identify as being vision impaired or blind. One of those astronomers is Dr. Wanda Diaz. She's somebody who had a degenerative eye condition. She went blind in her 20s when she was doing her astronomy undergraduate degree at university. She decided she really wanted to keep going. She wanted to keep doing her research. She wanted to do a PhD, become a doctor. And to do this, she actually had to develop her own tools so that she could use her sense of hearing to continue to basically do her astronomy research. And she's actually managed to be quite a successful researcher by using these tools that she's developed herself. And Dr. Gary Ferrand is another really good example. So Gary's from Australia. Gary used to work as an X-ray physicist. He worked at synchrotrons and particle accelerators. When he lost his sight, again, due to a degenerative eye condition, he couldn't safely do his X-ray research anymore, but decided that he wanted to pursue his love of astronomy. And so Gary is finishing off his PhD at the moment. And again, to do a lot of his research, he's had to custom make the tools that he can use to incorporate audio into the way that he does his research. So both of these researchers have been really, really successful in what they've done, but the tools that they've needed to do their research in non-visual ways haven't existed. They've literally had to build these tools for their specific needs so that they could continue to do their research in ways that would work the best for them.
Yeah, thanks, Nick. And we'll talk a bit later about how we want to improve that situation so people do not have to reinvent these tools every time they start their projects. So Nick's outlined a clear advantage to exploring sound as a way to explore astronomical data sets, and that's to make astronomy more inclusive, particularly at the research end in this case. However, there's a huge amount of potential, as Nick already alluded to use sound to discover things in astronomical data. Our ears are very good at picking out signals from background noise, as Nick gave his example in the train station. And I want to give you a real life example of this, not from astronomy, but from another field of research to do with acoustics. Now, I'm not going to go into all of the complex details of the data set, but it takes a nice story. I recently met Stephen Barras at a workshop that Nick and I organized, who works in this process of turning data into sound. We use this term sonification. So if we say sonification, what we mean is taking some data and turning that into sounds. And he had some complex data sets that he was given. Now I'm showing a visual representation of this complex data set on the screen. It's very complicated. There's multiple dimensions. There's all sorts of wiggles. There's all sorts of different colors going on. It's very, very complicated, quite difficult to see what's going on. So Stephen was given two data sets like this one that should have been identical. And the people who recorded the data and produced the data and analyzed the data said, these are identical data sets. And Stephen developed a tool to take that data set and turn it into a 3D model that looked like a bell. So he printed one bell using the data set 1 and another bell using data set 2, remembering that these data sets were supposed to be identical, and that's what he was told by the people who made the data. But when you listen to the bells, we'll see what happens. So I'm going to try and play the sound. Nick can let me know if it doesn't come through. So there you heard bell 1 and then bell 2. Do it again. So I hope you agree, those two bells do not sound the same. So Stephen was told, something must be wrong with your bells, something must be wrong with the way you made these, but actually it transpired, it turned out there was something wrong with one of the data sets. So this discovery was made by listening to the data. Now, we don't always have to print bells. You can do this in a synthesized way. So rather than actually making physical models of bells, you can synthesize the sound on a computer but I think this is a nice example to demonstrate the kind of discovery one might make if we explore the data using sound rather than the standard approaches. So what we're going to do now is we're going to talk you through the various applications of both using sound and tactile models in the astronomy world, both for education and for research applications. But I've got a little warning, so I don't want anyone to be confused. We're not recording sounds from space. Sound doesn't travel through the vacuum of space. What we're doing is taking the light that's detected by various telescopes and cameras in different parts of the spectrum, radio wavelengths, optical spectrum, and we're turning the data that's recorded into sounds. That's what we're talking about for the sound. And also we'll be talking about turning the data into tactile models as well. So we're going to take you on a bit of a tour of the universe. We're going to start on the Earth, and we're going to visit the planets, then other stars, then the Milky Way, and beyond. And at each point in our journey, we're going to talk about the different projects around the world that are taking this multisensory approach to exploring astronomy. So we'll be starting on the surface of the Earth, and I will let Nic tell you about the first project we have for you today.
Okay, so the first project we wanted to share with you is called The Sky in Your Hands. It's a project developed by astronomers at the University of Valencia in Spain, and it's mostly for education and outreach. Now, this project developed a planetarium show to help showcase all the constellations that you would normally see in sort of a planetarium show, basically in a planetarium. The way they did this and the way they made it accessible is, as well as showing the constellations on the actual dome of the planetarium, every time a constellation appeared, they had directional sound to indicate where the constellation was, but they also 3D printed these beautiful tactile versions of the dome with the constellations laid out on them. And so the picture on the right shows one of these domes. It's basically a half sphere. It has raised bumps to indicate the stars. The larger the bump, the brighter the star in the constellation. It has the lines that connect those constellations together. And this is basically a one-to-one mapping of what would be visible on the surface of the dome of the planetarium. Okay, next, and again, still staying on the Earth, I'd like to really quickly tell you about the Audio Universe tour of the solar system, which is a planetarium show that Chris and I are currently developing, which will hopefully be released later this year in December. This is a planetarium show that uses sonifications created through a software package called Strauss, which has been developed by another researcher at the University of Portsmouth who collaborates with me and Chris as well. The planetarium show, the whole aim of this show is basically to present everything in an audio format that doesn't need the visuals. So basically somebody can just listen to the show and get everything they need to out of it, but there'll also be visuals that will be supplementary to that as well. What we wanted to show you was an example of this for this particular show, is one of the sonifications that we've created. The idea here is that we wanted an audio way of representing what it's like as the sun sets and the stars begin to appear in the night sky, because the sun's light is disappearing. It's not outshining those stars in the night sky anymore. And so what you'll hear is the sound as each of the stars appears in the night sky as it becomes visible. It'll be a louder sound for brighter stars, quieter sound for dimmer stars, and it'll be a higher pitched sound if the star is blue and a lower pitched sound if the star is red in color. So have a listen and see what you can hear. There's also a visual representation on top of this, so the stars will pulse as they appear in the image as well. So that really got quite busy towards the end, but that's because we have all of the fainter stars appearing as the sun's light completely disappears from the night sky as the sun dips down below the horizon.
Yeah, thanks, Nick, and thanks to James Tretford for putting that together. And indeed, we used real data, imagining ourselves at the Very Large Telescope in Chile. We used the real positions of the stars, the real brightness of the stars to make that sonification for you. So still imagining that we're on the Earth, I want to talk to you about one more project before we move on in our journey. And this one again is about looking up in the night sky and seeing what's out there. It's a little bit more complicated, this one, and it allows you to go a little bit deeper. This is a piece of software developed by a fantastic computer scientist in Australia called Yuma Decal. He happens to be blind, and he's developed this software that allows you to explore the night sky in a very accessible way. Now, there is a computer-based version of this, but the most exciting part, I would say, is the iPhone app. So you can take your phone, you can point it up to the night sky, and it will tell you, depending where you're pointing, it will read out to you which constellation you are currently pointing at. So if you're pointing over Orion, it'll say Orion. You move over to say Cassiopeia, it will read out Cassiopeia. And then you have the option to listen to the stars inside that constellation. So very similar to what you just heard, assigning different notes depending on how bright the star is or how red the star is. You can listen to the stars inside the constellation in an interactive way. But more than that, if you want to learn more about those objects that are in that patch of sky, you can zoom in, you can click on them, and you can, in a very accessible format, you can learn about the information that we have about those objects. And this software is connected to astronomical databases around the world, so you can learn everything there is to know about everything in the night sky. And Yuma hopes that eventually this tool will be used by people to make scientific discoveries, because you'll be able to access these amazing data sets, explore the data in a sonification format or a visual format, depending on your choice, and maybe you'll discover something that the professional astronomers have not produced. So that's an exciting opportunity with that piece of software. So let's say goodbye to the Earth, Nick, and move our way out.
So we're moving out into the solar system, of course. We're not going to go too far just yet. So obviously the solar system is pretty interesting. There are lots of other planets other than the Earth orbiting around our sun, and there are accessible ways to talk about these planets as well. So one project that does this, I think, really effectively is A Touch of the Universe, which is another project developed by astronomers at the University of Valencia in Spain. It's again mostly for education and outreach. What this group have done is they've made these beautiful sort of basketball-sized tactile models of the rocky planets in our solar system. So that's Mercury, Venus, and Mars, and also of the Earth's moon. And what they've done is they've taken some of the more prominent, more famous features on the surfaces of these planets. So on Mars, it's things like the Valles Marineris or Olympus Mons, the really, really big mountain. On the moon, it's famous craters and mountains. And yeah, they've stretched the features basically to make them more detectable using your fingertips. Because if you left these features at their real heights, they wouldn't actually be detectable at all. They'd be so slight that you wouldn't be able to feel them with your fingertips. So they've stretched everything. And so their hope is that they can get these resources out to children who are blind and vision impaired, but also to people with perfectly good vision as well, to help everybody learn about the solar system.
Great. Thanks, Nick. And I hope Nick will tell you the story about how I discovered something using tactile features on some of his models rather than looking at them. So thinking about the planets, I will introduce another project, this one again going back to the sound side of things. So this is called A4BD, short for Astronomy for the Blind and Disabled. It's been led from the University of Patras in Greece, but it's an EU-wide project. And there are several elements to this project, including making accessible ways for people to make their own observations with real telescopes and explore the data. But the part I want to talk about today, again, is an app. This time it's an app that's built for an Android phone. And this app allows you to explore images through sound with your fingertips. So you can take your phone, there's an image on your phone. You can move your finger around the image and you will hear sounds as different sounds as you touch different parts of the image. Touch a bright part of the image, you'll hear a brighter sound. If you touch a darker part of the image, you'll hear a quieter sound. If you touch a red part of the image, you'll hear a lower sound. If you touch a blue part of the image, you'll hear a higher sound. So it allows you to explore the different brightnesses and the different colors inside that image through sound with your fingertips. Now, of course, you could apply this to any image, and indeed the software does allow you to explore many astronomical images, but we're going to give you a little example of Jupiter while we're visiting the solar system. So I'm going to play for you now a little video clip. It's an excerpt from a tutorial put together by one of the developers. Don't worry too much about what he's saying, but hopefully you can listen to, as he moves his finger around the image of Jupiter, the different sounds that we get.
But of course, I will prefer to use sound recognition on Jupiter. So what actually happens here is that I swipe my finger across the screen and I get to hear the different sounds. One thing that must be quite obvious is how the volume changes when you go to the white zones, and how the volume lowers when we go to the darker zones, and how the volume changes when we go to the bright zones. So it should be easily understandable that this is an object that has successive changes of bright versus darker zones.
So there you heard Andreas exploring the image of Jupiter and detecting through sound the stripes that we see on Jupiter of darker stripes and lighter stripes of the gas that makes up Jupiter. So we're going to move away from the planets in the solar system and now think about other stars beyond our sun. And when it comes to sound, there's a particular type of object in space where sound is potentially very useful. And in fact, going back to Wanda Diaz, these are the type of objects that change with time, are the kind of objects that she was studying through sound. So these are called variable stars. These are stars that change in a noticeable fashion through time, maybe over the course of days or years. And the first example we want to give is a type of star called a cataclysmic variable star. These are very explosive type variations. So if you stare at the star over time, you suddenly get these explosive increases in brightness, and then it goes back down, and then explosively gets brighter again. And our understanding of these objects is it's not actually a single star, it's a pair of stars. One star that you might call a regular star, something like our sun, and next to it, a compact star that we call a white dwarf star. So this is a star that's further along in its life. And these white dwarfs have a strong gravitational field, and that means they can pull material off the neighboring star. And as that process happens, sometimes you get these big flares of brightness, increases in brightness of the star. And sometimes this is caused because the material gets so hot it ignites a nuclear reaction. So if you stare at this star with a telescope and you record how bright it is over time, you can see these changes in brightness. So I'm showing you one graphical version of an example cataclysmic variable star on the screen. It's a graph where the up axis tells you how bright it is and then how it changes with time. So it looks like these mountains, these hills going up and down through time. Now we've taken that data and we've turned it into sound. Now this piece of data you will hear was recording the star over several days, tens of days, but we've compressed that into a few seconds. So what you'll hear is sped up in time. So I'll play you this sound and hopefully you'll be able to hear how the star changes in brightness through time. So there, we turned the sound this time into a wind type noise. So as the wind sound got louder, that corresponds to the star flaring up. So hopefully you heard a few sort of more gentle flares and then a really big explosive flare. I'll play you that one more time. There you go. So I don't know about you, but for me, I have a much deeper appreciation of what's going on in that data by listening to it. And to be honest, it's a lot more fun than staring at a boring graph like the one on the screen. But there are other reasons that stars change in brightness, other exciting reasons. And then Nick.
There are, absolutely. So some stars will actually change in brightness because they have planets orbiting around them. So if you can imagine, if we're lucky enough to be looking at another star and everything is lined up correctly, sometimes we can see planets drift across the surface of those stars. So basically move across in front of them. As you can imagine, as that planet moves across in front of that star, it will cause the brightness of that star to drop. And you would also expect that planet, as long as it's in a stable orbit, to go past multiple times over the course of maybe several days or several months, depending on how quickly these planets are moving around. So when we observe these kinds of changes in brightness in stars, oftentimes we want to look out for patterns or repeated signals. In this case, it will be that planet passing in front, moving around, passing in front again, moving around, passing in front. And so, of course, in the same way that we were able to use sound to listen to the other cataclysmic variable, we can also use sound to listen to stars that change in brightness because they have planets orbiting around them. We call these planetary transits. So there's a particular project called Astronify. It's a US-based project at the Space Telescope Science Institute. And this one's actually mostly being used for research because they've identified that, in fact, it's really easy to listen out for repeated signals in data like this by using sound. And so we're going to play you an example of an extrasolar planet moving around another star, blocking out that star's light over and over again. So this will be a signal that's sped up. So we'll be listening to, I guess, Chris, is it several days or several weeks worth of data?
I will have to look at the graph. I can't remember.
Yeah, no, neither can I. But what we want you to do is have a listen, see how many planetary transits, how many dips in that data you can hear. So what you'll be listening out for is the signal dropping in tone. So it will be quite high and it'll go down and then it'll go back up again, then it'll go back down. We want you to try and listen out, see how many of those dips, how many of those transits you can hear. We're going to ask you to answer another Zoom poll. So just to make this fair, Chris, do we want to play that one more time?
Yeah, so the answers you can choose from, A will be 9, B will be 7, C will be 5, and D will be 3. So how many transits do you hear? Okay.
And we're going to be a little bit mean. We're not going to tell you the answer straight away. We're actually going to take a little bit of a break and then come back to you with the answer after that.
So please put in your answer. We're going to take a 5-minute comfort break. So we need to take 5 minutes away from the computer and we'll return in 5 minutes and we'll reveal the answer to the question.
All righty. So do we have an answer for the poll?
Is Bethany with us to reveal the results of the poll?
Oh, there we go. Okay. So are they right, Chris?
We have 84% said 7, 13% said 5, 4% said 3, and 2% said 9. So majority ruled with the right answer.
Yep. And so we can actually show you a plot of what that data would look like, plotted visually rather than the way we listen to it. some of you probably noticed that the overall sound was decreasing in pitch. And so you can see that in the plot. But you can also see these really abrupt dips as the planet passes in front of the star and sort of blocks out its light. And yeah, absolutely, there are 7 of those dips.
Okay, so we're going to take our step away again, and we're now going to think about our Milky Way galaxy as a whole. As I mentioned at the beginning of this talk, there are hundreds of billions of stars in the Milky Way galaxy. The sun is just one of those. And as well as the stars, there is gas and dust, and this is the material that also forms new stars. So we're going to think about some images that have been taken of the very center of our Milky Way galaxy from a range of different telescopes in different types of light. Like we talked about at the beginning, we can take pictures in different types of light. We're going to look at 3 images before then listening to all of those 3 images together in a sound version of those images. So firstly, let's talk through the images that we'll see here. So the first one was taken by the Hubble Space Telescope, probably the most famous telescope ever, in the near infrared. So that means colors just beyond red. So you can't see it with your eyes, but a little bit further than red. And the image, it's a rectangular image, and then there's lots of sort of wispy, what I think look a bit like cotton wool patches of yellow. And these are bright regions of gas that's been illuminated by stars that are forming in these regions. New hot stars are lighting up this gas. And you can just about make out some specks, individual points in the background, which are the individual stars. If we take the same patch of sky, but now a picture taken with the Spitzer Space Telescope, moving even further into the red, beyond the red, I mean, into what we call the mid-infrared. Now we have, someone chose it to be red. It's not really red, it's infrared. And we're seeing these wispy regions across the whole image. And now we can see more individual specks because the light from the stars in the background is able to get through that dust that's causing this wispy regions in the infrared. Most of the visible light is blocked by the dust, but this infrared light can just about penetrate through this dusty region that covers most of this image. And the third image is in the X-rays. Again, it's blue. I don't know why people think X-rays are blue, but that's the choice that was made. And in the X-rays, the most interesting thing for me is these regions of hot gas. It's glowing gas that's glowing in the X-rays. And in the bottom right-hand corner of this image, we see a particularly bright region of X-rays. And that is where the supermassive black hole is residing at the center of our Milky Way, surrounded by this hot X-ray emitting gas. So they're the 3 images that we're now going to listen to. This was put together by a project called A Universe of Sound, done in collaboration between a group of people called System Sound, based in Canada, in collaboration with NASA and the various telescopes. So they've taken many of these types of images and turned them into sound. But we're going to listen to those 3 images of the center of the Milky Way all together. Different instruments have been assigned to each image. And as we scroll through the image, we're going to hear from left to right. So the sounds are scrolling through the image from left to right. If you hear individual plucks of sound, that's the stars in the background. And then there's an underlying drone sound, which is these wispy gas material that I just described. And if you listen towards the end, you'll hear it get louder as we pass over that bright gas associated with the supermassive black hole. So here we go. Let's take a listen. have it. So I think the main purpose of this is really to translate that beauty that we can see in the image into sound. I think the sounds are also beautiful, and this allows us to enjoy and appreciate the beauty that there is up there in space, but not just through pictures, but also from sound. So moving away from our Milky Way galaxy and on to other distant galaxies.
Absolutely. And so I think I said this before, but we think there are something like 2 trillion other galaxies in the universe outside of our Milky Way. And each of those galaxies is unique, but astronomers also like to group them together based on common properties. So we like to look at galaxies that might all be red, or galaxies that might all be blue, or galaxies that have spiral arms like our Milky Way, or galaxies that are a little bit more elliptical or ball-shaped like the picture on the right-hand side. And there are a couple of projects that explore these various aspects of galaxies using tactile and audio. So the first is the Tactile Universe project, as well as AstroBVI. So Tactile Universe is a project that I lead out of the University of Portsmouth. We've written code for 3D modeling software that will take any black and white image and turn it into a tactile image. And the way these tactile images work is they take the pixels of the image. Where those pixels are bright, the tactile surface is really raised. Where the pixels are darker, the tactile surface is lowered, and the tactile surface scales between all the different shades of gray between those bright and dark pixels. And so what we end up with is these tactile versions of these really beautiful but quite complicated images of galaxies that you can run your fingertips across, and you can feel all of the same information about the shapes, changes in brightness that you would be able to see using your eyes. So this is mostly for education and outreach. We mostly use these models to talk to school children about galaxies and galaxy research. But we like to use these with people who are blind or vision impaired, but also people with perfectly good vision, because we think everybody can benefit from thinking about these images in a slightly different way. And because Chris prompted me before, I'll just give you a really quick example of how this can help everybody. So if we just jump back a slide really quickly, Chris. So the image on the right here is of an elliptical galaxy. And when we look at this, our eyes trick us into seeing something that's ball-shaped. So it kind of has the shape of a football or a rugby ball. And it looks like it has an edge. Whereas these galaxies don't actually have edges. What happens is there's lots of stars in the centers of these galaxies. The density of those stars gets less and less as we move towards the edge of these galaxies, until the edge basically becomes the surrounding space. So the surrounding space will have the same number of stars as, I guess, what you would think of as the edge of these galaxies. But when we look at these galaxies with our eyes, we see a definite shape. We see this round thing. Whereas when you feel a tactile image of these, there's no real edge. The tactile feel just kind of merges with the background. And that's a much better representation of how these galaxies are made up than you get with your eyes. Your eyes sort of trick you a little bit.
Absolutely, and I can concur that after studying galaxies for a long time, once I touched Nic's tactile models, I really now do have a better appreciation for what an elliptical galaxy is, thanks to using a different sense than just my eyes. So we have one more data set and one more sort of project we want to share with you before we kind of wrap up. Now, this is a mysterious object, and this is more from the research side of things. These objects we want to talk about are called fast radio bursts. Well, they're not really objects, they're signals that we detect at our radio telescopes. And as the name would have it, they're fast bursts of radio emission that arrive at the telescopes and last very short periods of time, a fraction of a second. Some of them, you just get one burst and that's the end of it. Sometimes you get these repeated bursts of radio emission. So these are called repeating. These are quite mysterious objects, and we still don't really understand exactly what they are. They're probably something to do with compact objects like black holes, but they're an active field of study. And we want to be able to detect these quickly and point our other telescopes to these same patches of sky to see if we can figure out what's going on. But this data can be quite noisy, and I've got some examples on the screen. So what you're seeing are 9 rectangles. Each rectangle is a one observation of the same fast radio burst. So it was looked at 9 times as displayed on the screen. And going across corresponds to time, and up corresponds to frequency or wavelength of the light. These rectangles mostly look like noisy squares, just a lot of noise. But if you look closely, some are easy than others. You see these bright streaks going through the rectangles, and that's the signal of the fast radio burst. And this is an example of something that you might be able to hear quite well. So we're going to play you a sonified version of these 9 data sets. So you hear one after the other. You'll hear a lot of noise, but if you listen closely, you'd hear that streak going through the data set. That's the burst of radio emission. So you hear 9, one after the other. See if you can hear those bursts of radio emission in the data. So there we go. There's another example which we're exploring for research purposes of this application. So the last thing we want to tell you about is where is this all going and what's next, and particularly from the sound side of things. Myself, Nic, along with some collaborators, ran a workshop a few weeks ago now, where we brought together astronomers who were building these tools to turn astronomical data into sound. And we brought in experts in sound perception and sound design, so we can have this discussion about the best approaches that we have moving forward, because we identified some key challenges that we want to address over the coming years. So one thing that we want to see happen is we can increase the number of vision impaired astronomers. Nic explained he's quite a rare example, and there are not many vision impaired astronomers in the world because they're having to create new tools and new methods for themselves every time. But if we can develop these techniques, make them more mainstream, more normal, then vision impaired people coming through the system can just grab these tools and get on with the job. And also, if we can take multisensory learning approaches in the classroom more common, for example, with tactile models or sound, then we'll get more used to exploring images and data with other senses than just our eyes. And the other challenge that we want to look at is untapping this potential for scientific discovery with sound. As we mentioned, we know there's potential there. There are examples where we could use sound for scientific discovery. But we need to think about the best ways of turning that information into sound. How can we make it efficient? How can we optimize how we do that process? So these are all ongoing areas of research. I'm excited to be part of that. And it was exciting to discuss these challenges and ways forward at this workshop. With that, I'll give you again our take-home message. So there's a huge potential for multisensory approaches to astronomy, education, and research. And there are benefits for both accessibility and scientific discovery. So for myself, thank you for your attention.
And thank you very much from me as well.
And I will pass over to Sam, I believe, and we'll be here to answer any questions you may have. Is you with us, Sam?
I am back with you. Sorry, my computer just crashed.
Yeah.
Literally as the talk was coming to an end. And unfortunately, I have lost the list of questions. I'm just trying to look. One very interesting question that came on early was the 2 data sets that you explained at the beginning.
Yes.
You could hear the difference by when you actually printed the 3D bell. Could you actually tell the difference by more traditional methods?
Yeah, so this is an interesting point. So in theory, yes. And when they went back to the data set and reanalyzed it, they realized there were differences. But I don't know the full details, but the methods that they were using before, the approaches they were taking on the computer to compare the data sets didn't distinguish these differences. So whatever process they'd done to compare the data sets, their standard methods didn't identify the differences. The sound identified the differences, and they have to go back again and create new methods. So computers can do it, but maybe new discovery comes through sound, because you don't necessarily know what you're looking for when you develop these computer algorithms that compare data sets.
And then a very similar question came in. I was almost going to give you these 2 questions together, which is this sonification process still very experimental, or is it actually becoming more mainstream? I mean, is it something that we're going to be using quite often to analyze data, or is this very much just when there's someone who knows how to do it, who's doing it?
Well, you've identified one of the things that we want to change. So at the moment, yes, it's mostly experimental. It's fairly niche, but that is something we want to change. We want to convince astronomers and wider beyond that, that there is potential in this. And that was part of what we discussed at this meeting. How can we turn something that's probably really effective, and some people have demonstrated it's effective, and make it mainstream? So I think we need to do some work to build the infrastructure to prove it works and it's effective, and then try and roll it out. And so one way we're looking at that is by working with the big observatories, such as the European Southern Observatory. I'm doing that, and the Space Science Telescope Institute in the US. That was Astronify. And if we build sonification as a standard way to download the data or listen to the data in these big astronomy observatories, that would be one way to make it more mainstream.
I think it's kind of important to add as well that when we think about it, so sound is all around us all the time. There are people whose job it is to basically design sound to convey information to us when it comes to products, for example. So the noise that a shaver makes when you're shaving your chin is very deliberately designed into that product by somebody to convey particular bits of information. It'll make a really different noise when you're trimming hair versus not touching hair. So there's this audio input in other aspects of I guess, stuff that we do without really thinking about it. And that's pretty mainstream, even if we're not aware that it's happening. So it really is just about a shift in the way scientists think about sound and the way we apply it to things.
Yes, I must admit, I was quite intrigued. I was listening to a radio program the other day, and they pointed out you can hear the difference between hot and cold water being poured into a glass, which I could, but I never knew. I never knew until someone played it to me. Oh, we've got another work. Have you tried sonifying the data from stars according to signals from astronomical measurements? Can you see this question as well on question? Sorry,
I don't see. Astroseismology measurements.
Astroseismology. So
yes. Yeah. So that's a very interesting application. So that's to do with how the sort of internal parts of the star are moving, and yes. So some people have done that. To just simply answer the question, that is a type of data set that naturally makes sense because it's something that changes with time, and anything that changes with time naturally makes sense to turn into sound.
Could sonification be used in other areas of physics, e.g. analyzing data from CERN, I suppose?
Yeah, do you want to take that, Nick?
Yeah, no, absolutely. I think, I mean, again, anything that happens over some period of time, you can definitely turn into sound. That's sort of the easiest kind of sonification that you can do. You could imagine though, so for things like particle cascades, so when you have particles colliding, you have lots of little bits kind of arcing off in different directions. You see these showers of different particles resulting from that. You could imagine turning that into a sonification as well. And you could probably use some spatial stuff in there as well to actually track the progress of those different particles as they split off and break away. I don't know whether that's a good answer or not.
Yeah,
a lovely answer.
Thanks, Nick.
To get away slightly from sonification, we have lots of questions coming in about how useful that can be. But what instruments were used to observe waves outside the EM spectrum? From anonymous attendee.
Sorry, can you repeat the question?
What instruments are used to observe waves outside the EM spectrum?
Sure. So you need to detect, we have specialist types of telescopes to detect different types of light. So we, for regular light, you have things called CCDs, like you have in your regular camera. We have things that are called bolometers that almost think more like for detecting infrared light. In the radio waves, it's more like sort of satellite dish type technology. So each type of wavelength of light, we build specialist types of cameras that are specifically designed to collect that light, record it, and then we process it.
I'd also like just to add, obviously, that the question actually did ask about non-EM waves.
Oh, sorry, I went beyond.
No, it's perfectly reasonable. I just actually reread the question myself and noticed.
Yes.
I suppose the only waves we actually measure at the moment would be gravitational waves.
That's right. Yes. Yes. So, in terms of thing about astronomy, most of the things we've studied to date have been the electromagnetic spectrum. But as you just said, outside of that, the newest exciting thing is gravitational waves. And that's fluctuations in space-time as space is compressed and moved by, for example, black holes that have collided together and send these ripples of fluctuations in space-time that come to Earth. And we can measure these using laser beams and effectively just measuring how long it takes a laser beam to go from one place to the other. If you change that space with a gravitational wave, it changes the time it takes.
Actually, this question, unfortunately, because I've had some technical difficulties, I've lost questions that were sent in during the talk. So luckily, I've remembered a couple of them, but one of them went missing. I can't remember who it was. But this one actually asked a very similar thing, which was, in my view, the tactical versions are likely to be language independent. However, false color and sounds are likely to be culturally dependent. I think the other question was asking about the fact we obviously use a particular, in the Western culture, we use a particular scale, sound scale. Can you see this as a set of educational tools that transcend cultural differences?
Yeah. Nick, do you want to say that?
Yeah, so this is actually something that came up in the meeting Chris was talking about a couple of weeks ago. There was actually a fair bit of discussion about the way different cultures perceive sound, what different cultures will see as comfortable sound to listen to, what they will see as uncomfortable sound, what kinds of scales or tonal changes will be more appropriate, what kind of instrument choices. Say if we're choosing a particular instrument to represent something, there are very Western instruments, there are very Eastern instruments as well. So some of this is going to be culturally dependent. Any project that wants to get out to as many people in the world as possible is going to have to be a little bit sensitive of cultural sensibilities, I guess. But yeah, I don't know, Chris, do you have?
Yeah, no, I think the point the participant raised as well is tactile communication might be less culturally dependent. It's not actually something I put a lot of thought into, but thinking about it on the fly, it might be true that sort of handling objects is something that crosses cultures more so than your choice of what kind of music and sounds you're used to listening to.
No, I think that is an interesting avenue. This is actually one that I thought of myself, which was someone else asked, do you need an echo-free environment, an anechoic chamber, to standardize the listening of sounds? And I noticed that when we were doing the poll, Chris, you have a pair of headphones on, a pair of cans, which obviously would probably give you a little bit of an advantage when listening to, you know, to really pick out the subtleties in the sounds. So how much does this affect, do you think?
Yeah, I think, yeah, this is an important consideration. And there's a sort of a related question about making choices about how you communicate the sounds that came up earlier. I think it depends on the application. So if you want to use the sound for scientific analysis, absolutely, you want the best quality sound you can have. You want to control for that. So you can imagine you're going to want headphones and really have a good environment. Now, if you're kind of just giving an entertaining show, then maybe these factors are less important. Maybe the exact choices you make to convert the data into sound are less important. So I think these things are often application dependent. And it's something, again, that we discussed in the workshop. If you're doing something to sort of inspire and communicate, it's more important that it sounds good and you get the message across. If you want something that's done for analysis, it's more important that you're able to analyze that data in an accurate way.
Oh, I think given that we're coming close to the end of our time, so I'm not sure how many more questions we'll have, but we've got another one coming in which I think is probably very useful. Can you recommend undergraduate societies for visually impaired students who study science and engineering?
Nick, it's more for you probably.
I'm struggling to think of anything off the top of my head. So I know the University of York recently had a vision impaired student go through their undergraduate program. I believe they were trying to set up a network like the one that you've described. I don't know how far that got, how successful that was.
Maybe we've identified something that needs to be done, and
yes,
maybe the IOP could help.
Well, as a branch, I would love to. Obviously, up here in the northeast, we are actually quite close to some very dark skies, And it would be lovely to have you all up here. And well, Chris is local. I know Nic actually comes up quite often. Maybe we could start a society or something. It would be something we'd certainly enjoy trying to set up. So there have been questions have been coming in fast and thick there. Right, I think actually we're getting very close to the end. There is just one question that might be worth actually finishing on, which is, could we please hear the 9 fast burst, the radio bursts again?
Yeah, now I have to press a few more buttons.
Well, I like to end you on, I like to talk you at the end here.
Give me a technical challenge at the end.
A little technical challenge, yeah, well,
Okay, let's see what we can
in
manage.
real life, this is easy, so hopefully it's good on.
Okay, here we go, I found it. Let's hear those fast radio bursts again. There we go. There they were. Thanks.
So I think one thing to say with that is you do have to get better at picking those out the more you listen to that, because I think that's the 5th or 6th time I've heard that now. And I think I heard most of them that time. Whereas, yeah, the first time I was only able to hear about half of them. So.
Okay, well, that is actually, I make that pretty much the end of the billing time. Unfortunately, normally we would all mingle around for a bit longer. Thank you very much for an incredibly interesting talk, Chris and Nic. Hopefully, as I say, as the Northeast branch, we're going full into setting up events and everything. We're trying to get back to real life just like everyone else. So yes, thank you again.
Thank you very much. It's been a pleasure.
Thanks, everybody.